What if everything we think we know about the beginning of the universe is wrong? What if the Big Bang, that moment 13.8 billion years ago when all of space, time, matter, and energy supposedly burst into existence from a single point, never actually happened? This isn't just wild speculation. Some of the brightest minds in physics are seriously questioning whether the Big Bang theory tells the whole story, and recent observations from the James Webb Space Telescope have only intensified this debate. Today, we're diving into one of the most controversial questions in cosmology, exploring alternative theories that could completely rewrite our cosmic origin story. If you're ready to question everything you thought you knew about how the universe began, make sure to subscribe to this channel and hit the like button. Your support really means a lot to me. Now let's begin. Before we explore what might have happened instead of the Big Bang, let's understand why this theory became so dominant in the first place. The Big Bang model didn't emerge from nowhere. It was built on solid observations that any alternative theory must also explain. In the 1920s, Edwin Hubble discovered that galaxies are moving away from us, and the farther away they are, the faster they're receding. This cosmic expansion was the first major piece of evidence suggesting the universe had a beginning. Then came the discovery that changed everything. In 1964, Arno Penzias and Robert Wilson accidentally detected a faint microwave signal coming from every direction in space. This cosmic microwave background radiation, or CMB, is exactly what you'd expect to find if the universe was once extremely hot and dense, then expanded and cooled over billions of years. It's like finding the heat signature from an explosion that happened long ago, seemingly ironclad evidence for the Big Bang. The abundance of light elements provides another crucial piece of evidence. Our universe contains about 75% hydrogen and 25% helium by mass, with trace amounts of lithium and beryllium. Big Bang nucleosynthesis, the theory of how elements formed in the first few minutes after the Big Bang, predicts these exact proportions. It's hard to explain this precise ratio without a hot, dense beginning to the universe. But here's where things get interesting. The James Webb Space Telescope, our most powerful eye on the cosmos, has been sending back images that don't quite fit the standard Big Bang narrative. JWST has discovered massive, mature galaxies existing just a few hundred million years after the supposed Big Bang, galaxies that should have taken billions of years to form according to our models. Some of these galaxies appear as massive as the Milky Way, but existed when the universe was supposedly just a cosmic infant. These observations have reignited interest in alternative cosmological models. One of the most intriguing is the steady-state theory, first proposed by Hermann Bondi, Thomas Gold, and Fred Hoyle in 1948. In this model, the universe has no beginning and no end. It has always existed and always will. As galaxies move apart due to expansion, new matter spontaneously appears to fill the gaps, maintaining a constant density throughout space and time. The steady-state model elegantly sidesteps many philosophical problems with the Big Bang. There's no need to explain what came before the beginning, because there was no beginning. There's no singularity, that problematic point of infinite density and temperature where our physics breaks down. The universe simply is, has always been, and always will be, with matter continuously created at a rate of about 1 hydrogen atom per cubic meter every billion years. But the steady-state model faces serious challenges. The cosmic microwave background radiation is nearly impossible to explain without a hot, dense phase in the universe's past. The model also struggles to explain why we see evolution in the universe, why distant galaxies look different from nearby ones, why quasars only existed in the early universe, why the universe appears to have changed over time. If the universe is truly in a steady state, everything should look the same regardless of when or where we observe it. This led to a modified version called the Quasi-Steady state theory, developed by Jayant Narlikar, Jeffrey Burbidge, and Fred Hoyle in the 1990s. This model proposes that the universe undergoes cycles of expansion and contraction with periodic creation events that produce matter and energy. These mini-bangs could explain the cosmic microwave background and the evolution we observe while maintaining an eternal universe without a singular beginning. Another fascinating alternative is the cyclic or oscillating universe model. In this scenario, the universe undergoes endless cycles of expansion and contraction, big bangs followed by big crunches, forever. Each cycle might last trillions of years, with the universe expanding, reaching a maximum size, then contracting back to a hot, dense state before bouncing back into another expansion phase. The cyclic universe model gained new life in the early 2000s when Paul Steinhardt and Neil Turok proposed a version based on string theory. In their model, our universe exists on a three-dimensional membrane, or brane, floating in a higher dimensional space. Parallel to us is another brane, and these two branes collide periodically, perhaps every trillion years. Each collision appears to us as a big bang, releasing enormous energy and creating matter and radiation. Between collisions, the branes slowly drift apart, corresponding to our universe's expansion and eventual cooling. This ekparotic model, named after the ancient Greek word for conflagration, solves several problems with the standard Big Bang. It explains why our universe is so flat and uniform without requiring cosmic inflation, that period of exponential expansion in the first fraction of a second after the Big Bang. The collision of branes naturally produces the right conditions. It also avoids the singularity problem, since the branes never shrink to a point. They remain extended throughout the collision. Recent observations have provided intriguing, though not conclusive, support for cyclic models. Roger Penrose, the Nobel Prize-winning physicist, claims to have found evidence of Hawking points in the cosmic microwave background, circular patterns that could be the signatures of supermassive black hole collisions from a previous cosmic cycle. While other scientists remain skeptical of these findings, they've sparked renewed interest in the possibility that our Big Bang wasn't the beginning, but just the latest in an eternal sequence. Let's explore another mind-bending possibility: the plasma cosmology, or electric universe theory. Pioneered by Nobel laureate Hannes Alfvén and developed by physicists like Eric Lerner, this model suggests that electromagnetic forces, not gravity, dominate the large-scale structure of the universe. In this view, the universe has always existed as a vast plasma, electrically charged gas, with electric currents flowing through space on enormous scales. Plasma cosmologists argue that many cosmic phenomena attributed to dark matter and dark energy can be explained by electromagnetic forces. Galaxy rotation curves, the formation of galactic filaments, even the cosmic web itself might be shaped by electric currents rather than gravitational attraction alone. Laboratory experiments with plasma have produced structures remarkably similar to galaxies and galaxy clusters, suggesting that what we see in space might be electromagnetic phenomena scaled up to cosmic proportions. The plasma cosmology model doesn't require a Big Bang. Instead, the universe has always existed in a state of dynamic equilibrium, with electromagnetic forces creating and destroying structures over vast timescales. The cosmic microwave background, rather than being relic radiation from a primordial explosion, might be the result of ongoing processes in the plasma that fills intergalactic space. However, plasma cosmology faces significant challenges. It struggles to explain the precise blackbody spectrum of the cosmic microwave background, the observed abundance of light elements, and the time dilation we observe in distant supernovae. Most cosmologists consider it a fringe theory, though its proponents argue that mainstream science is too wedded to the Big Bang paradigm to fairly evaluate alternatives. Another alternative that's gained attention recently is the rainbow gravity theory proposed by physicists Adel Awad and Ali Farag Ali. This theory modifies Einstein's general relativity by suggesting that gravity's effects on space-time depend on the energy of the particles involved. Just as a prism splits white light into a rainbow of colors, gravity might affect high-energy particles differently than low-energy ones. In rainbow gravity, the universe could be infinitely old. The Big Bang singularity disappears because different wavelengths of light experience time differently near the supposed beginning. What looks like a singularity in standard relativity becomes a region where time stretches infinitely for certain particles. The universe might have always existed, with what we call the Big Bang being just a phase transition rather than a true beginning. The implications are profound. If rainbow gravity is correct, the universe might be filled with particles that have existed forever, carrying information from an infinitely distant past. Black holes might not have true singularities at their centers, but rather regions where space-time is radically, but not infinitely curved. The theory makes testable predictions about how light from distant gamma-ray bursts should behave, and some observations hint at effects consistent with rainbow gravity, though the evidence remains inconclusive. Perhaps the most radical alternative is that our entire universe is a simulation. While this might sound like science fiction, serious physicists including Neil deGrasse Tyson, Max Tegmark, and late Stephen Hawking have suggested it's worth considering. If our universe is a simulation, then the Big Bang might simply be when the simulation was switched on, or when our particular subroutine began running. The simulation hypothesis could explain some puzzling features of our universe. Why do we have a cosmic speed limit, the speed of light? Perhaps it's the maximum processing speed of the system running our simulation. Why is space-time quantized at the Planck scale? Maybe those are the pixels of our simulated reality. The fine-tuning problem, why physical constants seem perfectly calibrated for life, makes sense if someone deliberately programmed these values. The simulation hypothesis gained unexpected support from an unlikely source, the study of black holes and information theory. The holographic principle, developed by Gerard 't Hooft and Leonard Susskind, suggests that all the information in a volume of space can be encoded on its two-dimensional boundary. This is exactly how computer graphics work: three-dimensional worlds encoded on two-dimensional screens. If our universe is holographic, it's remarkably similar to a cosmic computer simulation. But let's return to observational evidence that challenges the Big Bang. The lithium problem has puzzled cosmologists for decades. Big Bang nucleosynthesis predicts that the early universe should have produced a specific amount of lithium-7, but when we observe ancient stars, they contain only about 1/3 of the expected amount. This discrepancy has resisted all attempts at explanation within the Standard Model. Either we don't understand stellar physics as well as we thought, or something's wrong with our picture of the early universe. The horizon problem presents another challenge. Different regions of the cosmic microwave background have almost exactly the same temperature, about 2.725 Kelvin, even though they're so far apart that light couldn't have traveled between them in the age of the universe. How did these regions coordinate their temperatures if they've never been in causal contact? The standard solution is cosmic inflation, but that requires accepting that the universe expanded faster than light for a brief period, which seems like special pleading to some physicists. Speaking of cosmic scales and distances, if you're fascinated by just how vast our cosmic neighborhood really is, check out my video, How Far Does Our Galaxy Actually Reach? You'll discover that the Milky Way's influence extends far beyond the stars we can see, reaching out with invisible arms of dark matter and magnetic fields for millions of light years. The link is in the description and on the card above. The flatness problem adds another layer of mystery. Observations show that our universe is geometrically flat within a fraction of a percent. But flatness is unstable, like balancing a pencil on its point. Any slight deviation should grow over time. For the universe to be this flat after 13.8 billion years, it must have been flat to an extraordinary precision at the Big Bang, about 1 part in 10 to the 62. This seems impossibly fine-tuned, unless there's some mechanism we don't understand. Recent observations of enormous structures in the universe challenge the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. The Hercules Corona Borealis Great Wall, a galactic superstructure spanning 10 billion light-years, is so large it shouldn't exist if the universe is only 13.8 billion years old. There simply hasn't been enough time for gravity to organize matter on such scales. The Methuselah star, catalogued as HD 140283, presents an age paradox. Using stellar evolution models, astronomers calculated its age at 14.5 billion years, older than the universe itself. While refined measurements have brought this down to about 13.2 billion years, the margin of error is uncomfortably small. Finding stars nearly as old as the universe suggests either our age estimates are wrong or stars formed much earlier than the Big Bang model predicts. Let's examine the variable speed of light, VSL cosmology, proposed by João Magejo and Andreas Albrecht. In this model, the speed of light was much higher in the early universe and has been decreasing over time. This would solve the horizon problem naturally. Regions of the universe could have been in causal contact when light traveled faster. It would also explain the flatness problem and potentially eliminate the need for cosmic inflation. VSL cosmology makes testable predictions. If the speed of light changes over time, fundamental constants like the fine structure constant should also vary. Some observations of distant quasars hint at such variations, though the evidence remains controversial. The theory suggests our universe might be much older than 13.8 billion years, with the apparent age being an artifact of assuming constant light speed. The conformal cyclic cosmology proposed by Roger Penrose offers yet another alternative. In this model, the universe goes through infinite cycles, but not through expansion and contraction. Instead, the infinite future of one universe becomes the Big Bang of the next through a mathematical transformation called conformal rescaling. When the universe becomes cold and empty in the far future, with only photons remaining, it becomes mathematically identical to a hot, dense Big Bang. This model predicts that signals from the previous universe, or aeon, should be visible in our cosmic microwave background. Penrose claims to have found such signals, circular patterns he calls Hawking points, where the evaporation of supermassive black holes from the previous aeon left their mark. While controversial, these claims have sparked serious investigation into whether we can detect evidence of a universe before the Big Bang. The emergence of quantum gravity theories has opened new possibilities. Loop quantum cosmology based on loop quantum gravity suggests that the Big Bang singularity is replaced by a big bounce. As we trace the universe backward in time, instead of reaching infinite density, quantum effects cause gravity to become repulsive at extremely small scales, causing a bounce from a previous contracting universe. Loop quantum cosmology makes specific predictions that differ from the standard Big Bang model. It suggests that before our expanding universe, there was a contracting universe that reached a minimum size, not zero, but about the Planck length, before bouncing back. This previous universe would have left signatures in the cosmic microwave background, particularly in the form of specific patterns in the polarization of this ancient light, Some researchers claim to have found hints of these patterns, though the scientific community remains divided. The black hole. Cosmology hypothesis proposes something even more radical. Our entire universe exists inside a black hole in a higher dimensional parent universe. This idea, developed by physicists like Nikodem Popławski, suggests that every black hole contains a universe, and our Big Bang was actually the formation of a black hole in another cosmos. The mathematics work surprisingly well. The equations describing the interior of a black hole are remarkably similar to those describing an expanding universe. This model explains several puzzles. The universe's apparent fine-tuning might result from selection effects. Only universes with the right properties produce black holes that spawn new universes. Dark energy could be explained by the rotation of the parent black hole. The arrow of time might be determined by the direction of matter falling into the black hole. We can never see outside our universe because we're inside an event horizon, a boundary that light cannot cross. Recent data from the Planck satellite has revealed anomalies in the cosmic microwave background that don't fit the standard Big Bang model. The axis of evil, a strange alignment of temperature fluctuations across the sky, suggests the universe might not be as isotropic as we thought. There's also the cold spot, an unusually large and cold region that's difficult to explain with standard inflation theory. These anomalies might be telling us something fundamental about our cosmic origins. The mirror universe theory, proposed by physicists from the Perimeter Institute, suggests that the Big Bang created two universes simultaneously, ours running forward in time and a mirror universe running backward. This CPT symmetric model, charge parity time, naturally explains several mysteries, including dark matter, which might be ordinary matter in the mirror universe, interacting with us only through gravity. The Big Bang becomes less of a beginning and more of a reflection point between two temporal directions. Let's consider what the James Webb Space Telescope is really showing us. The discovery of massive galaxies like Glass Z12 and Sears 93316 existing just 300 to 400 million years after the supposed Big Bang challenges our understanding of structure formation. These galaxies aren't just big, they're surprisingly mature, with evidence of multiple generations of stars and possibly even supermassive black holes at their centers. The impossible early galaxy problem has cosmologists scrambling for explanations. Either galaxies formed much faster than we thought possible, dark matter behaves differently than expected, or our estimates of the universe's age need revision. Some physicists are proposing modifications to general relativity that would allow faster structure formation. Others suggest primordial black holes formed directly from density fluctuations rather than stellar collapse might have seeded early galaxy formation. The tired light hypothesis, first proposed by Fritz Zwicky in 1929, offers a completely different interpretation of cosmic observations. Instead of galaxies receding due to expansion, perhaps light loses energy as it travels through space, shifting toward the red end of the spectrum. Modern versions propose mechanisms like photon-photon scattering or interaction with quantum vacuum fluctuations. While most astronomers reject tired light because it can't explain time dilation in supernovae, some researchers argue these objections might be overcome with more sophisticated models. String theory opens up possibilities for entirely different cosmic histories. In the string gas cosmology model, the universe began in a hot, dense state where all 9 spatial dimensions predicted by string theory were compact and equal in size. Through a process called decompactification, 3 dimensions expanded to become our familiar space, while the others remained microscopic. This model doesn't require a singularity and naturally explains why we have 3 large spatial dimensions. The emergent universe scenario suggests that our universe emerged from a static, eternal state rather than a singularity. In this model, the universe existed forever in a dormant condition, perhaps as a quantum fluctuation that didn't collapse before transitioning to expansion. This avoids the philosophical problems of creation ex nihilo from nothing, while still accounting for the expansion we observe today. Recent studies of quasar light passing through intergalactic gas clouds have revealed unexpected patterns. The Lyman alpha forest, absorption lines from neutral hydrogen, shows correlations across vast distances that shouldn't exist if the universe evolved as the Big Bang model predicts. Some researchers interpret this as evidence for a fractal universe with self-similar structures at all scales, incompatible with the homogeneous Big Bang model. The discovery of coherent orientations in quasar polarization across billions of light-years challenges the cosmological principle. If the universe began from a single point, there should be no preferred directions in space. Yet observations suggest that electromagnetic fields might be aligned across cosmic scales, implying either a pre-existing structure before the Big Bang or fundamental physics we don't understand. The concept of eternal inflation adds another twist to our cosmic story. Proposed by Alan Guth and others, this theory suggests that inflation, the rapid expansion of space, never completely stops. While it ended in our observable universe, creating what we call the Big Bang, it continues elsewhere, constantly spawning new pocket universes like bubbles in an infinite champagne bottle. Our Big Bang wasn't the beginning of everything, just the beginning of our particular bubble. This multiverse scenario radically changes the question, what if the Big Bang never happened? In eternal inflation, Big Bangs are happening all the time, everywhere, forever. Our universe becomes just one of infinitely many, each with potentially different physical laws and constants. The fine-tuning problem dissolves. We observe the constants we do because only universes with these values can support observers like us. Recent observations of the cosmic web, the largest structure in the universe, reveal patterns that seem too organized for the time available since the Big Bang. The South Pole Wall, discovered in 2020, stretches 1.4 billion light-years across. Computer simulations struggle to produce such massive structures in just 13.8 billion years without invoking exotic physics or modifying our understanding of gravity and dark matter. The MOND theory, modified Newtonian dynamics, and its relativistic extension, TVES, propose that gravity itself behaves differently on cosmic scales. Rather than invoking dark matter to explain galaxy rotation curves and cluster dynamics, these theories modify how gravity works at very low accelerations. If correct, this would fundamentally alter our understanding of cosmic evolution and potentially extend the age of the universe. Let's examine what happens to fundamental physics if there was no Big Bang. Without a beginning, the second law of thermodynamics, which states that entropy always increases, faces a paradox. In an eternal universe, entropy should have reached its maximum long ago, resulting in heat death. Various solutions have been proposed. Perhaps entropy can decrease locally while increasing globally, or maybe the universe has mechanisms for resetting entropy that we don't understand. The information paradox takes on new dimensions in a universe without beginning. Information, according to quantum mechanics, cannot be created or destroyed. But if the universe had a beginning, where did all the information encoding the laws of physics, particle properties, and cosmic structure come from? An eternal universe sidesteps this problem. Information has always existed, but raises the question of why this particular set of information rather than another. Recent developments in quantum cosmology suggest that asking, what came before the Big Bang, might be like asking, what's north of the North Pole? A meaningless question based on false assumptions. Time itself might have begun with the Big Bang, making before a nonsensical concept. But this leads to its own problems. How can time begin? What determines the initial conditions? Why these particular laws of physics? The holographic universe theory, supported by theoretical work in string theory and observations of black hole physics, suggests our three-dimensional universe might be a projection from information encoded on a two-dimensional surface. If true, the Big Bang might be an illusion, a three-dimensional interpretation of a more fundamental two-dimensional process that has no beginning or end in the traditional sense. Observations of cosmic voids, vast regions with few galaxies, challenge Big Bang predictions. The KBC void in which our local group resides spans 2 billion light-years. Such enormous voids shouldn't exist if matter was distributed evenly after the Big Bang and had only 13.8 billion years to cluster. Either our understanding of structure formation is flawed, or the universe's history is different than we think. The axis of evil in the cosmic microwave background remains one of the most puzzling observations in cosmology. This unexpected alignment of temperature fluctuations with our solar system's orientation suggests either an incredible coincidence, systematic errors in our observations, or fundamental physics we don't understand. Some physicists propose it's evidence that our universe is finite and smaller than we think, with patterns repeating due to light circumnavigating the cosmos. Recent analysis of type Ia supernovae, the standard candles used to discover dark energy, has revealed potential problems. Different research groups get slightly different results for the universe's expansion rate, a discrepancy known as the Hubble tension. This might indicate that our cosmic distance ladder is flawed, dark energy changes over time, or our basic cosmological model needs revision. The sterile neutrino, a hypothetical particle that could explain various anomalies, might revolutionize cosmology if discovered. These particles could account for dark matter, explain matter-antimatter asymmetry, and alter our understanding of the early universe. Some interpretations of neutrino oscillation experiments suggest sterile neutrinos exist, though confirmation remains elusive. Quantum entanglement experiments have revealed that information can be correlated across any distance instantaneously, though no information can be transmitted faster than light. Some physicists wonder if the universe itself might be entangled, if distant regions share quantum correlations from a common origin. This could explain the universe's large-scale uniformity without requiring a Big Bang or inflation. The discovery of dark energy in 1998 revolutionized cosmology, but it also deepened the mystery of our cosmic origins. If dark energy is the cosmological constant Einstein proposed, it has remained perfectly constant for billions of years, an extraordinary coincidence. Alternative theories suggest dark energy might be dynamic, changing over cosmic time. If it was different in the past, our calculations of the universe's age and history could be completely wrong. Quintessence theories propose that dark energy is a dynamic field that evolves over time, possibly even changing from attractive to repulsive. If dark energy was weaker or absent in the early universe, structures could have formed faster, resolving the impossible early galaxy problem. Some models even suggest dark energy could reverse, eventually causing the universe to contract, perhaps cycling eternally without ever having a true beginning. The Penrose diagram technique, which maps infinite space-time onto a finite diagram, reveals something profound about the Big Bang's singularity. In these diagrams, the Big Bang looks suspiciously similar to the infinite future of an empty universe. This mathematical similarity inspired Penrose's conformal cyclic cosmology. Perhaps what we call the Big Bang is just a transition from one cosmic epoch to another with no true beginning. Recent observations of galactic magnetic fields challenge Big Bang timeline predictions. Magnetic fields in galaxies billions of light-years away are surprisingly strong and organized. Creating such fields requires dynamo processes that should take billions of years, yet we see them in galaxies that supposedly formed shortly after the Big Bang. Either magnetic fields form much faster than we thought, or they're primordial, existing before galaxies formed. The cosmic neutrino background, if we could detect it, would tell us about the universe when it was just 1 second old. But here's the catch. Some alternative cosmologies predict different neutrino backgrounds or none at all. The fact that we haven't directly detected these relic neutrinos leaves room for models where the early universe was radically different from Big Bang predictions. Let's explore the philosophical implications of a universe without beginning. The Big Bang gives us a creation moment, a clear before and after that satisfies our intuition for cause and effect. Without it, we face an infinite regress. Every moment has a predecessor, every cause has a prior cause, stretching back forever. This isn't necessarily impossible, but it challenges our deepest assumptions about the nature of existence. The anthropic principle takes on new meaning in an eternal universe. If the universe has always existed, why do we find ourselves at this particular moment? In an infinite timeline, any finite period, including the one containing human civilization, has probability 0. Some philosophers invoke the Boltzmann-Brane paradox. In an eternal universe, it's more likely that you're a random fluctuation of particles that briefly forms a conscious brain with false memories than a real being in a coherent universe. Recent studies of cosmic topology suggest our universe might have a non-trivial shape. If space curves back on itself like a hypertorus or has more exotic topology, light from distant objects could reach us via multiple paths. Some anomalies in the cosmic microwave background might be the same regions seen from different directions. A finite but boundless universe eliminates the need for a beginning. It simply exists like the surface of a sphere has no edge. The vacuum catastrophe, the 120 order of magnitude discrepancy between predicted and observed vacuum energy, might hint at fundamental flaws in our cosmological model. If we can't explain why empty space has the energy density it does, how can we claim to understand the universe's origin? Some physicists suggest this catastrophic failure indicates we need entirely new physics, possibly including a different cosmic history. Observations of quasars challenge the standard timeline in multiple ways. Some quasars host supermassive black holes of billions of solar masses when the universe was supposedly less than 1 billion years old. Growing such monsters requires either seed black holes far more massive than stellar collapse can produce, or growth rates exceeding theoretical limits. Direct collapse of primordial gas clouds might work, but this requires conditions difficult to achieve in standard Big Bang models. The lithium problem has gotten worse with better observations. Not only do old stars have less lithium than Big Bang nucleosynthesis predicts, but the deficit varies between different stellar populations in ways that make no sense. Some globular clusters have even less lithium than field stars of the same age. Either stars destroy lithium through unknown processes, or our understanding of the early universe needs major revision. String theory's landscape of 10 to the 500 possible vacuum states offers a radical reframing. Perhaps universes with different physical laws are constantly being created through quantum tunneling between vacuum states. Our Big Bang might have been just such a tunneling event from a parent universe with slightly different physics. In this view, Big Bangs are common, but the Big Bang, a unique beginning of everything, never happened. The trans-Planckian problem questions whether we can trust any theory about the universe's beginning. During inflation, quantum fluctuations that seeded cosmic structure would have started smaller than the Planck length, where our physics breaks down. How can we base cosmology on processes we fundamentally can't describe? This isn't just a technical detail, it suggests our entire framework might be flawed. The recent crisis in cosmology extends beyond theoretical concerns to fundamental observations. The JWST has discovered not just mature galaxies, but entire galaxy clusters in the early universe. The SPT234956 protocluster contains over a dozen massive galaxies undergoing rapid star formation when the universe was supposedly just 1.4 billion years old. The coordination required for such structures challenges our understanding of how fast gravity can work. Dark matter's role becomes even more mysterious if the Big Bang never happened. In the standard model, dark matter helps explain how structures formed so quickly after the Big Bang. But if there was no beginning, dark matter might be something entirely different, perhaps ordinary matter in parallel dimensions, or a manifestation of modified gravity on cosmic scales. The bullet cluster collision, often cited as proof of dark matter, might have alternative explanations in non-Big Bang cosmologies. The cosmic web's filamentary structure shows remarkable mathematical properties. These filaments follow log-normal distributions and display fractal characteristics across scales from megaparsecs to gigaparsecs. Such mathematical regularity suggests underlying organizational principles that might predate any Big Bang. Some researchers propose the universe has always been organized this way, with matter flowing along eternal cosmic highways. Recent detections of ultra-high-energy cosmic rays pose timeline problems. The GZK cutoff should limit how far such particles can travel, yet we detect them from sources that, given the universe's supposed age, shouldn't be able to reach us. Either these particles violate known physics, or the universe's history is different than we think. Some exotic particles might be relics from pre-Big Bang physics. The problem of cosmic coincidences becomes acute without a beginning. Why is the universe flat to 1 part in 10 to the 60? Why are the strengths of fundamental forces so precisely balanced? With a Big Bang, we can invoke inflation or anthropic selection. In an eternal universe, these coincidences demand explanation. Perhaps they're not coincidences, but necessary relationships we don't yet understand. Quantum gravity effects might eliminate the need for a beginning entirely. In theories like causal set theory, space-time is fundamentally discrete, made of distinct points with causal relationships. In this framework, the Big Bang singularity can't exist because you can't compress discrete points to infinite density. The universe might have always been a growing network of causal relationships with no first moment. The information paradox deepens when considering cosmic origins. The universe contains vast amounts of information, from the precise values of physical constants to the detailed structure of galaxies. Information theory suggests this can't arise from nothing. An eternal universe sidesteps this by having information always exist, but raises questions about why this particular information content rather than another. Observations of cosmic rays from active galactic nuclei reveal acceleration mechanisms that challenge our understanding. Some particles reach energies that would require accelerators larger than our solar system. If such extreme physics is possible now, what might have been possible in other cosmic epochs? The universe's capacity for extreme phenomena suggests our models might be too conservative. The measurement problem in quantum mechanics takes on cosmic proportions. If observation collapses wave functions, who observed the early universe to give it definite properties? Without observers, the universe should remain in superposition. Some physicists propose consciousness is fundamental to the cosmos, others that decoherence doesn't require observers. Either way, the Big Bang's quantum state remains mysterious. Recent studies of galaxy morphology reveal unexpected patterns. Spiral galaxies in the early universe show the same winding patterns as modern ones, despite having less time to develop. The handedness distribution of galaxies shows slight asymmetries that shouldn't exist if the universe began from a symmetric state. These observations hint at pre-existing structure or organizational principles beyond our current models. The dark flow phenomenon, galaxies moving coherently toward a point beyond our observable universe, suggests influences from regions we can't see. If confirmed, this would mean our observable universe is just part of a larger structure, possibly infinite, with no meaningful beginning. The Big Bang becomes a local event in an eternally existing cosmos. Time crystals discovered in 2016 show that perpetual motion is possible in quantum systems. These structures repeat in time without energy input, challenging thermodynamics. If time crystals exist, why not space-time crystals, cosmic structures that repeat eternally without beginning or end? The universe itself might be a vast space-time crystal, oscillating forever. The holographic principle's implications become stranger in eternal cosmologies. If our 3D universe encodes information on a 2D surface, what about time? Perhaps our experience of temporal flow is also holographic, a projection from timeless information on the cosmic boundary. The Big Bang might be where our holographic projection begins, not where reality itself starts. Observations of primordial black holes, if confirmed, would revolutionize cosmology. These wouldn't form from stellar collapse, but from extreme density fluctuations in the early universe, or in alternative models, from pre-Big Bang physics. The recent gravitational wave detections include black holes in the mass gap, where stellar evolution shouldn't produce them, possibly indicating primordial origins. The discovery of gravitational waves has opened an entirely new window into testing cosmic origins. LIGO and Virgo have detected mergers of black holes with masses that challenge stellar evolution theory. Some of these black holes are too massive to form from stars in the time since the Big Bang. They might be primordial, formed from direct collapse of matter in conditions that standard Big Bang models can't easily explain, or they might be remnants from a previous cosmic cycle. The nanograv collaboration's potential detection of a gravitational wave background suggests the universe is filled with low-frequency ripples from countless massive black hole mergers. But the signal is stronger than Big Bang models predict. This excess might come from cosmic strings, theoretical defects in space-time from phase transitions, or from processes in alternative cosmologies we haven't considered. Let's examine the vacuum stability problem. Measurements of the Higgs boson mass suggest our universe exists in a metastable state. We're in a false vacuum that could decay catastrophically. But we've existed for supposedly 13.8 billion years without decay. In eternal universe models, this stability problem becomes acute. Perhaps vacuum decay has happened, and we exist in a bubble of new physics, making our Big Bang a local vacuum transition rather than a universal beginning. Recent observations of fast radio bursts reveal cosmic structures we don't understand. These millisecond pulses of radio waves come from billions of light years away, some repeating in patterns that defy explanation. If they're from exotic objects like cosmic strings or domain walls, they might be relics from physics beyond the Big Bang paradigm. The universe might be filled with phenomena from epochs or physics we haven't imagined. The cosmic opacity problem challenges Big Bang timeline assumptions. In the Standard Model, the universe became transparent to light about 380,000 years after the Big Bang when atoms formed. But observations of distant quasars show the universe was more opaque than expected at certain wavelengths until much later. Either our understanding of cosmic chemistry is wrong, or the timeline needs revision. Artificial intelligence analysis of cosmic data has revealed patterns humans missed. Machine learning algorithms studying galaxy distributions find correlations extending beyond what Big Bang models predict. These might be mathematical artifacts, or they might indicate real cosmic structures requiring new physics. AI doesn't share human preconceptions about cosmic history, potentially revealing truths we're biased against seeing. The multiverse implications of eternal inflation challenge the uniqueness of any beginning. If inflation spawns infinite universes, each with its own Big Bang, then asking about the beginning becomes meaningless. It's like asking for the first number in an infinite sequence. The question assumes a structure that doesn't exist. Our Big Bang becomes just one event in an infinite ensemble. Recent studies of cosmic topology using the cosmic microwave background have found hints that the universe might be finite but multiply connected. Like a video game where exiting one side brings you back on the other, space might wrap around itself. In such universes, there's no edge, no center, and potentially no beginning, just eternal existence in a finite but unbounded cosmos. The entanglement structure of the universe provides another angle on origins. Quantum field theory suggests the vacuum state is highly entangled across all scales. This entanglement might be primordial, not created by the Big Bang, but existing eternally. Some physicists propose space-time itself emerges from entanglement, making the Big Bang an emergent phenomenon rather than a fundamental beginning. Observations of ultra-diffuse galaxies challenge formation timelines. These galaxies are as large as the Milky Way but contain only 1% as many stars. Standard models struggle to explain how they formed and survived. They might be failed galaxies from different cosmic conditions, or evidence that galaxy formation follows multiple pathways we don't understand. The cosmic ray anisotropy problem reveals unexpected structure. Ultra-high energy cosmic rays should come uniformly from all directions if the universe is isotropic. Instead, we see slight preferences for certain directions, suggesting either local sources we haven't identified or large-scale structures beyond our models. The universe might be fundamentally anisotropic, contradicting Big Bang assumptions. Recent developments in loop quantum cosmology provide specific predictions for what replaces the Big Bang singularity. The theory predicts a big bounce at a specific density, about 41% of the Planck density. This isn't arbitrary but emerges from the quantum geometry of space. If confirmed, it would mean the universe has always been cycling, with each bounce slightly different due to quantum fluctuations. The dark energy coincidence problem becomes more acute in alternative cosmologies. Why does dark energy have roughly the same density as matter right now when we happen to exist? In an eternal universe, this coincidence seems impossible. The two densities evolve differently and should almost never be comparable. Unless there's a mechanism maintaining this balance, our existence at this precise cosmic moment defies probability. Observations of the Lyman alpha forest in quasar spectra reveal the universe's chemical evolution doesn't match predictions. The abundance patterns of elements in gas clouds billions of light-years away suggest either stellar evolution works differently than we think, or the universe's history differs from Big Bang models. Each anomaly adds weight to the possibility that our cosmic story needs fundamental revision. The recent discovery of coherent magnetic fields spanning millions of light-years challenges everything we thought we knew about cosmic evolution. The Abell 3266 galaxy cluster shows organized magnetic structures that should have taken longer than the universe's supposed age to form through standard dynamo processes. These fields might be primordial, existing before galaxies formed, suggesting a pre-Big Bang origin or fundamentally different physics in the early universe. Quantum information theory provides a radical new perspective on cosmic origins. If information is more fundamental than matter or energy, then the universe might be computational at its base. The Big Bang becomes less a physical explosion and more an information-theoretic event, perhaps the booting up of a cosmic computer. This isn't a simulation hypothesis, but something deeper. Reality itself might be information processing, with no need for a physical beginning. The sterile neutrino anomaly, if confirmed, would require new physics beyond the standard model. Experiments like Miniboon and LSND hint at neutrino oscillations that shouldn't exist, possibly indicating a fourth neutrino type. These particles could have dominated the early universe, changing its evolution completely. They might even compose dark matter, rewriting our understanding of cosmic structure formation. Recent analysis of the cosmic web using persistent homology, a mathematical technique from topology, reveals structures that seem too regular for random formation. The voids and filaments follow mathematical patterns suggesting underlying organizational principles. Some researchers propose these patterns are eternal, with matter simply flowing through pre-existing geometric structures rather than creating them. The black hole information paradox takes on new dimensions when considering cosmic origins. If information can't be destroyed, where was it before the Big Bang? Stephen Hawking's final papers suggested information might be stored on holographic screens at black hole horizons. Perhaps our universe's information was always encoded on some cosmic boundary, with the Big Bang being when this information began expressing itself in 3 dimensions. Observations of time dilation in distant supernovae confirm the universe is expanding, but also reveal puzzles. Some supernovae seem to evolve faster or slower than expected, even accounting for time dilation. This might indicate that fundamental constants like the speed of light have changed over cosmic time, invalidating our age estimates and suggesting a much longer or different cosmic history. The cosmic web's connectivity shows properties resembling neural networks. Using graph theory analysis, researchers find the universe's large-scale structure has statistical properties similar to biological neural networks and social networks. This isn't mysticism, but hard mathematics. The universe seems organized according to principles we see in complex systems that process information. Recent discoveries about quantum tunneling suggest our universe might have tunneled from a previous state rather than beginning from nothing. In quantum mechanics, systems can tunnel through barriers to lower energy states. Our universe might have tunneled from a higher energy vacuum state, making the Big Bang a phase transition rather than a beginning. This process could be eternal, with universes constantly tunneling to new states. The problem of cosmic magnetic monopoles illustrates how alternative cosmologies might solve Big Bang puzzles. Grand unified theories predict magnetic monopoles should have formed copiously in the early universe, yet we've never found one. Standard cosmology invokes inflation to dilute them, but alternative models might never produce them, naturally explaining their absence without special pleading. Dark matter's distribution in dwarf galaxies contradicts Big Bang predictions. These small galaxies should have dense, dark matter cores, but observations show constant density cores instead. This core cusp problem might indicate dark matter behaves differently than expected, or that galaxies formed through processes not accounted for in Big Bang models. The cosmic optical background, the total light from all sources, is twice as bright as the sum of known sources. This missing light problem suggests either we're missing major populations of objects, or light is being produced through unknown processes. In steady state or cyclic models, this excess light might come from matter creation or exotic physics we haven't considered. Recent studies of galaxy cluster collisions reveal dark matter behaves strangely. In some collisions, dark matter seems to lag behind regular matter, while in others, it doesn't. This inconsistency challenges the cold, dark matter paradigm essential to Big Bang cosmology. Alternative gravities or different cosmic histories might better explain these observations. The fine structure constant, which determines electromagnetic interaction strength, might vary across space and time. Observations of distant quasars suggest tiny variations, about 1 part in a million, but even this would revolutionize physics. If fundamental constants change, our calculations of the universe's age and evolution could be completely wrong. Cosmic voids are emptier than Big Bang models predict. These vast regions should contain a cosmic web of faint dwarf galaxies and gas, but many seem truly empty. Either our understanding of structure formation is flawed, or voids represent regions with different physics or cosmic history. They might be windows into alternative cosmological scenarios. The axis of rotation found in cosmic microwave background data suggests the universe might be rotating. This would violate the cosmological principle and require explanations beyond the Big Bang. A rotating universe might be eternal, with angular momentum preventing collapse or requiring modified physics we haven't discovered. As we reach the culmination of our cosmic investigation, let's confront the profound implications of questioning the Big Bang. Science isn't about dogma, it's about following evidence wherever it leads. The fact that serious physicists are questioning our cosmic origin story isn't a crisis but a sign of science working as intended. Every theory, no matter how well established, must continuously face scrutiny against new observations. The tension between quantum mechanics and general relativity becomes particularly acute at the supposed moment of the Big Bang. Quantum mechanics requires uncertainty, while general relativity predicts a singularity, a point of infinite density and zero size. These two pillars of physics are fundamentally incompatible at the moment of creation. Perhaps their conflict is telling us that there was no such moment, that the Big Bang as traditionally conceived is a mathematical artifact rather than physical reality. Recent philosophical work on the nature of time suggests that the flow of time might be emergent rather than fundamental. If time emerges from more basic quantum information structures, then, before the Big Bang, isn't meaningless, it's a different configuration of information. The universe might have always existed in a timeless quantum state, with time emerging alongside space when specific symmetries broke. The Big Bang becomes not a beginning, but a transition. The anthropic considerations take on new meaning in eternal cosmologies. If the universe has existed forever, then the probability of observing conditions compatible with conscious observers approaches unity. We exist because, in an infinite number of configurations across eternal time, observer-compatible conditions must eventually arise. The apparent fine-tuning of physical constants becomes statistically inevitable rather than miraculous. Recent advances in laboratory plasma physics provide glimpses into cosmic-scale phenomena. Experiments with ultra-intense lasers create conditions approaching those supposedly present nanoseconds after the Big Bang, but these experiments also reveal unexpected behavior, matter and energy configurations that our models didn't predict. If we can't fully understand conditions we can create on Earth, how confident can we be about the cosmic origin story? The discovery that time might be quantized, existing in discrete chunks at the Planck scale, fundamentally changes questions about beginnings. If time is digital rather than continuous, asking about the first moment is like asking for the smallest positive number. Between any two moments, there's always a previous moment. The Big Bang might be unreachable, always one Planck time away, no matter how far back we trace. The cosmic microwave background, long considered the smoking gun for the Big Bang, might have alternative explanations we haven't adequately explored. Some researchers propose it could be thermalized starlight from an eternal universe, radiation from matter, antimatter, annihilation in steady-state creation, or even the glow of quantum vacuum fluctuations amplified by unknown mechanisms. Each hypothesis deserves rigorous investigation rather than dismissal. The Hubble tension, the disagreement between different methods of measuring cosmic expansion, might be telling us something profound. Local measurements using supernovae and Cepheid variables give one value, while calculations from the cosmic microwave background give another. This discrepancy could indicate that space expands at different rates in different regions or epochs, that our universe isn't homogeneous, or that our entire cosmological framework needs revision. Recent discoveries in quantum field theory suggest the vacuum is far more complex than we imagined. It's not empty, but filled with virtual particles, quantum fields, and possibly hidden dimensions. This seething quantum foam might be eternal, with our universe representing one particular excitation of underlying quantum fields that have always existed. The Big Bang becomes a dramatic reorganization rather than creation ex nihilo. The observation of mature galaxies at high redshifts has reached critical mass. It's not just one or two anomalies, but a pattern emerging from JWST data. Galaxy after galaxy appears too massive, too mature, too structured for its supposed age. While astronomers scramble to modify formation models, perhaps we should question whether our age estimates are fundamentally wrong. An older or eternal universe naturally explains these observations. The role of consciousness in quantum mechanics, the measurement problem, scales up to cosmic questions. If observation collapses wave functions, then the universe requires observers to become definite. But the Big Bang supposedly happened before any observers existed. Some interpretations suggest the universe retroactively became definite once observers emerged, while others propose consciousness is fundamental and eternal, as old as the universe itself. Looking at the forest rather than individual trees reveals a pattern. Every aspect of Big Bang cosmology faces challenges. The singularity problem, the horizon problem, the flatness problem, the magnetic monopole problem, the lithium problem, the Hubble tension, the impossible galaxy problem, each has proposed solutions, but together they suggest something systematic is wrong with our framework rather than individual details needing refinement. Yet we must acknowledge what alternative cosmologies must explain. The cosmic microwave background is real and requires explanation. The universe is expanding. We observe galaxy redshifts and time dilation in distant supernovae. Light element abundances closely match Big Bang predictions. Any alternative must account for these observations, at least as well as the standard model. Perhaps the answer isn't choosing between Big Bang and alternatives, but recognizing that both frameworks might be incomplete. Reality could be more nuanced, a cyclic universe where our Big Bang was real but not unique, an eternal multiverse where Big Bangs constantly occur, or something we haven't imagined because our minds are trapped in either-or thinking. The atoms in your body were forged in stellar furnaces regardless of whether the universe had a beginning. You are made of stardust whether the cosmos is 13.8 billion years old or eternal. The questions we ask about cosmic origins are part of what makes us human. This drive to understand not just how things work, but how everything began, where we came from, where we're going. Science progresses by questioning, testing, and occasionally overturning even our most cherished theories. Newtonian mechanics reigned for centuries before Einstein revealed its incompleteness. We thought the universe was static and eternal until Hubble showed it's expanding. The Big Bang model has served us well for decades, explaining vast swaths of observation. But science isn't about protecting theories, it's about understanding reality, whatever that requires. As you contemplate these cosmic possibilities, remember that not knowing is okay. In fact, not knowing is where science begins. Every great discovery started with someone brave enough to say, "I don't know, but let's find out." The Big Bang might be correct, or it might be the next theory awaiting its successor. Either way, the journey of discovery continues. The universe doesn't care what we believe about it. It simply is, operating according to laws we're still discovering. Whether it began 13.8 billion years ago or has existed eternally, whether it emerged from a singularity or bounced from a previous cycle, it has given rise to galaxies, stars, planets, and consciousness capable of pondering its own origins. So what if the Big Bang never happened? Perhaps we'd find ourselves in an eternal cosmos where creation is continuous, where every moment contains both infinite past and infinite future. Or perhaps we'd discover something even stranger, a universe that defies our categories of beginning and eternal, operating on principles our evolved brains aren't yet equipped to grasp. The only way to know is to keep observing, keep questioning, and keep reaching for understanding. The journey to cosmic truth continues. New telescopes peer deeper into space and time. New theories push the boundaries of imagination. New observations challenge old certainties. And through it all, humans, star stuff, contemplating stars, continue the ancient quest to understand the cosmos and our place within it. That quest itself, regardless of the answers we find, might be the most profound expression of what the universe can do. Create beings capable of asking why. If you made it this far, make sure to subscribe to the channel and give the video a thumbs up. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. Light speed versus warp speed. Which one really wins? If you're fascinated by interstellar travel, the future of space exploration, quantum physics, and the deepest mysteries of the cosmos, this video is for you. See you there.